Wednesday, the principal component analysis will not be part of this exam. Does that make sense? Okay, I want to welcome you to my lecture today. Principal, I call this application of principal component analysis. Of course, we started this Wednesday, where I walk you through some properties of principal component analysis. So in the outline, walk you through the application in real life. Of course, we have the principal component analysis as interpretability issue. I'm actually going to walk you through the interpretability limitations in this lecture. And how do we improve on the interpretability? I'm actually going to walk you through that in this lecture today. Then I'm going to walk you through some illustrative examples. Now, application in real life. Of course, I remember on Wednesday, I walk you through the application of principal component analysis in real life. I think the major intention here is how we can reduce the dimensionality in our data set. With our times we work with data set, there are so many features. So how do we actually reduce the features in a way that we actually going to retain significant features with significant contribution, okay, in terms of variance maximization. I told you the other time, variance maximization in principal component actually correspond to largest information. So I told you, I gave you an example from gene expression, when we talk about the genome-wide association studies where you got a lot of, features of genes, and you want to partition individuals into cluster individual with similar genetic structure, okay? You want to be able to like figure how, what are the most important genes, that are needed for that regard. I also talk about storage, storage, when you take a look at image compression, you never take a look at your image, okay? The dimension of the image is determined by pixels, and the more the dimension of the image, the more the storage facility that you actually need. And we don't have unlimited storage facility, and therefore something needs to be done to reduce the dimensionality in the data set. So we use it to reduce dimensionality. We also use it when you reduce dimensionality, you are reducing noise in the process, because you actually eliminating features with a less significant contribution. So, and the moment you do that, the moment it is no longer noisy, you can actually visualize. It will allow what I call easy visualization, because when you have data set high dimensional, of course visualization is going to be an issue. And I also talk about face recognition and so on like that. I'm actually going to say this, principal component analysis, has a wide range of application from agriculture to zoology. Now, I want to talk about the interpretability limitations. The other time I said that we actually want to produce principal components, even though we still have information retained for original variables. Each principal component is still going to be a linear combination of the original variables. But despite that, okay, there's going to be a loss of interpretation for the original variables, because what we're working with now, we now work with principal components, okay, and interpreting the principal component may be kind of tedious in a way, because we're no longer working with the original variable. So, if we want to, we normally take a caution, we carefully interpret, the linear combination. And another reason why, interpretability has a limitation with principal complement analysis because of the what I'm going to call abstractness of principal component. Let me tell you this. Principal components are not the real factors. They are abstract. They actually provide us the direction, of the high dimensional data set. They only talk about the direction. Okay, they are not the real factors because they are not the real original variables. That's what I mean. And that's what I call them they are abstract. Okay, so that is another reason why the interpretation may be difficult. Then another reason why interpretation may be difficult is what I'm going to call sign ambiguity. Sign, positive or negative. Let me tell you this. When I run this analysis, maybe a particular variable in this analysis may have a positive sign. When I run another analysis with the same data set, a variable that has a positive sign here, that same variable may have a negative sign in another, analysis. So that is what I call sign ambiguity. That's one of the reasons why there is a limitation in interpretation. And another reason that I'm actually going to call is when you have high dimensional data set of, where you have so many features. Okay, when you have so many features, even though the principal component analysis enable us to reduce, but the facts remain, we cannot eat our cake and still have it. I'm talking about the same cake that you eat. Okay, so there's always going to be a dimensionality trade-off. Does that make sense? So we actually got a lot of reason for that. But let me tell you this. We acknowledge the fact that we got limitations in interpretability, but we have ways to improve interpretability. Otherwise, if there's no way to improve its interpretability, what is the essence? So one of the ways in improving interpretability is what I call rotating the principal components. Rotating the principal components will enable us to redistribute the variances of the principal component, and we're going to do that in factor analysis. Okay, after the midterm, there's going to be another topic that we call factor analysis that will enable us to do that rotation, and with that, it will make the principal component analysis to be more interpretable. Then another thing that make it interpretable is we examine the loadings. Today, I'm going to show you loadings. The loadings are more or less like the magnitude of the coefficient. Don't forget, every principal component has a linear combination of the original variables. There's going to be some loadings that will act as the magnitude of the coefficient. So if I really want to know what is the contribution of this original variable to the principal component, the loading is going to help us out. Does that make sense? Then I'm also going to use something today that will enable us to improve on the interpretability. It's what we call biplots. Biplots. Look at the word biplot. It means we're plotting two things at the same time. You know what we're plotting? Number one, we're actually going to plot the principal component on that. We're also going to plot the data itself, the original variable itself. That's what we call biplots. Okay, so the biplot will enable us, for easy visualization and interpretation, which I'm actually going to be walking you through right now. Now, let's go into illustrative example. Now, on illustrative example, of course, I said if you want to work with principal component analysis, we actually need to be able to decide, am I going to work on covariance, or am I going to work on correlation? Okay, And I said, we actually choose, the only reason to choose covariance is when, the features are the same units. But the moment they have different units, because we don't want a situation where a particular feature will dominate, maybe because of its range, because of its units, because of its scale, then we're actually going to use correlation in that regard. Because the correlation is when you modify covariance, it's what we call correlation. So we can use between the covariance and correlation depending on the nature of the features, whether they have the same unit or not. Okay. Now I want to go into example now. Let me tell you this principal component analysis has wide range of application, very useful in sport analytics, where you want to compare the performance of countries in sports, like in the recently concluded Olympics in France, in Paris. I think the next Olympic is going to be where? That's what I tell me. Those of you who follow sports. It's going to be the next Olympics is taking place in the United States. Is it Los Angeles? I think Los Angeles is hosting it. Yeah. So if you want to know the performance of countries or players in sports, the different sport they play, there's so many sporting events, and I remember a particular event in Olympics where an athlete will participate in maybe 7 or 8 events. Can somebody remind you, those of you that do sport, is it a platon or something? Somebody, just one person will participate in so many, and they will be counting points. And if they want to rate those players, those athletes, like if there's so many events, we don't want to use so many features. How do we use some few features, that will make sense? The principal component analysis is going to work. Now take a look at this example. The data set come from Besson and Hymas in 1984. This is a record for 55 countries. 55 countries in the following mass track events: 100, 200, 400, 800, 1,005, 5,000, 10,000 meters and marathon. Of course, here now, maybe we want to look at the performance of countries, 55 countries, men in track event. Don't forget the features here. The event is ranging from 100 to marathon. Now, what we want to, if you take a look, the data are in seconds for the first 3 events. Why in second? Those ones are sprints. 100, okay, 200, 400. All those events, they are measured the time in seconds. Okay, I remember what is the name? Usain Bolt. I remember this American guy. Oh my God, why? I remember is it Shakira? I was recounting. I remember all of that. That is in seconds, and 5,000, 10,000, maybe others ones are in minute. They just wanted to. But you know what? Before we can think of whether we should use principal component analysis, we must have sensed a problem. And if I want to go by John Tukey in 1970, John Tukey in his paper on data exploratory analysis, when he said, before we do anything on data set, before we get to know our data set, before we do whatever with our data set, we need to get to know our data set, by doing a detective work, where we try to have a graphical investigation where we exploit our data set. That's exactly what I'm trying to do here. Can we have a way to see if the variables here are correlated? Because it is when variables are correlated, then the idea of principal component analysis is going to work, converting correlated variables to uncorrelated. Don't forget, I told you the other time, I said the principal components as they are orthogonals. What do I mean by orthogonality is that the features are going to be independent at the end of the day. Initially, originally, they were, we got some kind of correlation between them. And you know what? If we want to do that, we're actually going to draw a scatter plot. We want to be able to see the relationship. It's going to be a pairwise relationship. Don't forget, we got so many variables. We want to compare them one at a time. And of course, if you take a look at the one in the diagonal, okay, if you look at the one in the diagonal, oh my God, the one in the diagonal is what we call the histogram. That is just to give us the sense of the probability distribution of that. In statistical analysis, we care about the distribution of data to see whether it's normal or not. Now, you know what we're trying to do here. Now, I need you to pay attention now. I need you to pay attention now. I did not provide any hard code in this lecture material, and the hard code will be in the lab, okay? But I want to assume that we have used an hard code, and you know what I'm trying to show you right now? I want to show you loadings. Now, this particular, I use covariance matrix. Why do I use covariance matrix? Maybe because, oh my God, 100 meters, 200 meters, 400 meters, 800 meters. They are all in meters, right? They are all the same units. I can use covariance matrix. Okay, but if they are not in the same unit, I'm actually going to use correlation matrix. So right now, using the coding out, I was able to generate a principal component based on covariance. Now I need you to pay attention. This has selected two principal components. Because I told you the other time, the number of principal components we want to arrive at should be less than the numbers of features. You remember I said when we have P, numbers of features, okay, where we want to have K, numbers of principal components in such a way that K is less than P. Does that make sense? Now, right now, what I'm trying to display to you right now is to show you that we selected two principal components, maybe because they gave the largest information based on threshold. That's actually going to walk you through. But in each of the principal components, you're actually going to have original variables. Do you see original variables? Now, those values that you are seeing right now, we call them loadings. Okay, those values that you see, we call them loadings, and they give us what I call the measure correlation between the principal components and the original variables. I'm going to say that again. Those values that you see right now, give me 1 second. I'm actually referring to these values. For principal component 1, that measures correlation between the original variable and that particular principal component. Okay, we call them loadings. And not only that, they also give us the contribution of the original variable to the principal component. And you know what? The possible values, what is the range? From -1 to +1. Does that make sense? Because they are correlation values. -1 to +1. Now, if you take a look at the principal components too as well, okay, you also got some loadings. Okay, so those are called loadings. Is there any question about what I just explained right now? Any question on this? Okay, now you know what we mean by loadings, right? Those guys are loadings. Okay, if it's very close, if loading is very close to 1, okay, that is actually telling you, you have a very strong positive relationship, very close to -1. Okay, you have very strong negative relationship. I think you understand that. Now, You know, I told you the other time it may be difficult to interpret principal component analysis, but you know what? Examining the loadings will enable us to do to do that. Okay, examining the loadings. We're examining the loadings right now. Now, let me tell you this. I'm going to tell you this. This is giving me a sense. I need you to take a look at this guy. Oh my God. This is giving me a sense that principal component number one is about marathon. Focus more on marathon. Why is it focused on marathon? Look at that. Negative is 0.97, even though we know the principal component, they are abstract. They are not the real factor, but because of the way the magnitude of the marathon, then it's trying to say, if I want to talk about something that has to do with marathon, the principal component one will do the job. Am I making sense? That is what the guy is trying to say. And oh my God, look at this guy. If I want to talk about 400 meters now, the focus should be on principal component two. Look at that. Now, another way how to be able to address the interpretability issue with principal component, we normally consider what we call a biplot. We got two types of biplots. Do you know the one I'm showing you right now? The biplot here is actually compute, this is a graph that plotted the principal component 2 against principal component 1. And not only that, I need you to pay attention to this. Oh my God. I'm seeing United States here. Those are the participating countries. Those are the data point. The biplot will actually indicate the position a particular data point is to the origin. When some, and it's also going to give us information about those ones that cluster together, maybe they have similar, those are the countries that have similar performance. They cluster together. Okay. Now, when you see a country like this guy, give me 1 second. Like if you take a look at this guy, our United States, in terms of performance, what happened? They got a very huge gap, right? So the biplot will enable you to be able to see relationship in terms of relationship between the data point, because in this case, countries are the data point. The way they cluster together, the way they are far from each other, and you know what? Those points, they are projected into the principal component space. Don't forget, you can see what I plotted on the y-axis and on the x-axis. Okay. Now, you know the other time I used covariance, right? Okay. This is the result of using correlation matrix for the same problem. And what I'm trying to say, there's possibility actually going to have different results. Okay. But when do we use one? When all the variables have the same unit, go for covariance. But where they have different unit, go for correlation. Does that make sense? Let me tell you this. At times, it's going to look as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. Because we got a provision in statistics and machine learning world. This is for this situation, use this. For that situation, use that. If you make an attempt not to follow the rule, then whatever information that we got from whatever model we use will mislead. Does that make sense? Now, I'm going to move right now. Okay, this is projection based, or this is a biplot that shows, the plot between the two principal components and the data point, the countries, when we make use of correlation matrix. I showed you the other time when we make use of covariance. Okay, another thing is, another issue, How many principal components should we keep? We should have a rule. I've been showing you two principal components, but we need to have a rule that will guide us. How many should be appropriate? But let me tell you this, for visualization purpose, we normally like 2 or 3, because anything more than 4, it may not be easy to visualize. Does that make sense? Okay. And we also going to, if we want to talk about selection now, don't forget the other time I talked about eigenvalues. The eigenvalues are the variances, right? The variances of principal component. Of course, the eigenvalue corresponding to principal component 1 will be the largest. But what you want to do, we can do cumulative. We want to know the percentage of variance explained. If you take a look at what I'm trying to show you now, if I want to look at a particular principal component, okay, and I want to know what is the percentage of variance explained in general, don't forget what we're going to have in the denominator is actually going to be the addition of all the variances, right? Like total variance. Now I really want to know what is the percentage of variance explained by this particular principal component. I'm actually going to do the ratio. Okay, and you know what? We actually going to make use of this guy for a pre-specified small value alpha. At time we could use 0.1. Okay, we're going to base it on that. And we also have another way we do able. Oh my God. You remember when we're dealing with the clustering, we use able as one of the criteria for choosing the optimal numbers of clusters. It's also going to take a center stage here, but we call that screen plots. Okay, we can look at the screen plot to be able to know what is going to be the optimal. Okay, but let me tell you this. I said some hypothesis tests have been proposed, but there is no universal rule. So we say, okay, cumulatively 80%, at least 80% would be fine. Some may say 85%, some could say 90. Okay, but research is all ongoing. But let me show you the screen plot. Oh my God! Look at the screen plot. You can see the principal component 1 is the biggest, right? It's always going to be. Do you know I can decide to say, okay, I'm only keeping 1 and 2 here based on what I'm seeing right now? Does that make sense? You know, if I don't want to use 3 to whatever, those ones are small. Those ones will look like features with less important contribution. I'm only want to retain, the one with a significant contribution. Take a look at that. Okay, now how do we compute the principal components? Okay, mathematically, this is how we do that. We can, and the singular value decomposition is going to play a role. But you know what? We got a way to do this now. Don't be scared. I'm just trying to explain that. Now take a look at this. In practice, don't forget, we want to work. I said in practice, the covariance or correlation matrix is not used in practice. The way we normally start, if you want to start from first principle, where you have your data X, right? You have your data X, matrix X, and it is equal to U, D, V, the transpose of that. You remember singular value decomposition, okay? Now, so now, if you want to compute the variance, if take a look at this, what we're trying to tell the world is that if I know V, the square of D and the transpose of V, that is going to be the same as the n minus 1 multiplied by the estimate of the sample covariance. And you know what? The question is, what is V? Oh, V contains the eigenvectors, okay, of the sample covariance, okay, and D square is eigenvalues. Okay, you know, the other time we've done eigenvalues. Oh my God. The eigenvalues, they are the variances of the principal component. Why the eigenvector, we're actually going to have for a particular eigenvalue, there will be corresponding eigenvectors. Oh my God. The eigenvectors will be the loadings. I'll show you the other time. Okay, I want to move away from mathematical jargons now. Okay, okay, so some other issues. Do you know at times we could have principal components that have the same variances? Situation where all the eigenvalues are the same. What do we expect? Initially, we expect the first principal component to have the largest, right? And it's going to be going in decreasing order. But at times, we could have situations where they all have equal, where where the eigenvalue coincide. Okay? And you know what? That's going to be an issue. But we have a way to do that. Now, I want to say this. PCA is not robust to what I call, I said PCA is not a robust method. Therefore, it's sensitive to outliers. Okay? But let me tell you, don't be scared. We got some robust version of PCA. We do research every day to improve on it. Okay? Now, subset of variables, then singular, the most important thing is this. Singular variance covariance. When determinant of a variance covariance is 0, you know what happened? Mathematical issue. Okay? When the determinant of variance covariance matrix 0 is going to be singular, which means before you can get the eigenvectors or eigenvalues from a matrix, that very matrix must not be singular. Does that make sense? So singular means the determinant is going to be 0. I'm talking about the determinant of the variance covariance itself. Okay. I think I've demonstrated this to you, of course, in stock markets. We could have, for instance, okay, let me quickly address the population versus sample PCA. Okay, in statistics, we have population parameter, we have statistic as well, right? We may not have access to the whole population. We normally end up, investigating sample. It means if this guy is a population variance covariance, then what we need is the sample variance covariance because we're working with sample data. And let me tell you this, the eigenvalues and eigenvectors of the variance, the estimate of the variance covariance is expected to approximate the true variance covariance. The true variance covariance is the population of variance covariance. Of course, in statistics, we have been able to prove beyond every reasonable doubt that an estimator, okay, an estimator can actually be used to approximate the population parameter. You've done all of that in statistical inference, in sampling distribution, demonstrating that, the consistency of an estimator. I mean, how many of you of us that 4102 theory of statistics? How many? You've heard on theory of statistics? Theory of statistics 4101 and 4102 or 5101 or 5102. Okay. Okay. And it will be problematic. This is going to work so great when the number of observation is more than number of features. What if in a situation where this happen? Maybe the number of features is 1,000 and the number of observation is 100. We normally observe this in stock market. Okay. Now there's going to be an issue here, but we have a way to deal with it. Okay. Let me quickly move. I need you to take a look at the script plot here. The sample size that you use matter. Take a look at when you have 1,000, when you have 100, and when you have 20. Okay, this will show you we got different standard deviations from when you have 100, from you have 100, 1,020. Okay, you know what I want to do now? I want this thing to make more sense. I want to use, the other time we use sports example. I want us to go into city example. Let's say around. We want to talk about crime. Okay, are you ready? Are you good to go, right? Let's talk about crime. But don't go into crime. We just want to talk about crime. Okay, so city crime data. We got some crime variables here like murder, rape, robbery, and so on like that. And of course, maybe we got a lot of cities. We got cities. Okay, now this is a piece what I'm actually going to call a pairwise scalar plot. We actually want to see the relationship between the original variables, and not only that, we want to see the probability distribution for each of that. That's why we are doing this. Now, after using principal component analysis, we retain 3 components. You can see 3 principal components with each loadings. Okay. Now, when you take a look at these loadings, you're actually going to see, for instance, if I want to talk about rape, I want to award an extra credit now. If I want to talk about rape, which principal component out of the 3 do you think I should be focused on? If I want to talk about rape, based on what you are seeing right now, go ahead. Exactly. Send me a message for extra credit. That is principal component number 3. Why? Take a look at that. Compare that. You see? If you compare that. Okay? So just take a look at that. And do you know, I told you a biplot. Okay? Another way to cluster. If you take a look at this biplot right now, some city that are very close, that they have the same crime characteristics. Take a look at that. Okay, when cities are close together, okay, when they are close together, they share similar characteristics. That's all it means. That's what this picture is showing in terms of the characteristics of interest. Cities that are far from each other, like Newark, Oklahoma, take a look at that. Okay, it means they are not clustered together. When you want to talk it means they have high degree. The crime rates in those 2 cities is very, very great. Does that make sense? It's different. The disparity in crime rate. But when they are clustered together, okay, they actually share this similar experience in terms of the characteristics of interest. Now, how do I decide on the number of principal components to retain? Here I got 4. Okay, the first principal component has this as a standard deviation. How do I get the standard deviation for each of them? Oh my God, that is the square root of each eigenvalue. Don't forget, eigenvalue is variance, right? Each eigenvalue represents variance. What is the square root? Standard deviation. We have this as standard deviation. You can see this is what we expect when the variance is going down. The standard deviation also needs to be going down. Now, we can talk about the proportion of variance right now. So when you take a look at this, the proportion of variance for each of the principal components is what we have right here. Okay, don't forget, how do I get 0.54? 1.948 divided by the totality. That will give you each of that. Now we want to look at it cumulatively now. Okay, when you take a look at these 2, they cumulatively explain 71% of the total variance. And that may not be good enough because some researchers want at least 80. Okay, now take a look at this guy now. If I want to get at least 80, I'm actually going to go all the way to 3 because cumulatively, the 3 principal components explain 82%. Does that make sense? Okay, because of my time, I'm actually going to move. This is a mathematical principle around the biplot. In principal component analysis, biplot is very, very crucial. Okay, away from this now, I want to quickly show you how we make use of angles in a biplot, how we make use of angles, how we make use of the data point, how we interpret all of that. Because of that, I will go to Canadian. Let me come to the Canadian data. I'll go to Canadian data. Give me 1 second. Okay. I'm going to put a lot of example. I want to go to Canadian data. I want to talk about Canadian temperatures and cities in Canada. Okay. I want to be able to see. Maybe we got a lot of features. We want to use principal component analysis. And at the end of the day, we're looking at, okay, the original variables of interest, they are months, January to December. Those are the variables. And the number of observation is the number of weather stations in Canada. Take a look at that. Okay. 12 variables, 12 original variables, 12 features. The number of weather stations in Canada, 35. When we use principal component analysis, okay, you're actually going to see the contribution of principal component 1. Okay, if I use principal component 1 only, if I use the combination of the two, that will give me 97.2%. Now, I'm going to show you something now. I'm going to show, because of the fact that, depending on what I want, okay, if I want to retain all of this, like, 99.15%, if I want to use the 3, this is going to be the corresponding loadings. Now, what are the variables now? Original variable, don't forget I said months. Okay, I need to take a look at that. But there's something I want you to pay attention now. I want you to pay attention now. I want you to look at the biplot. Let's take a look at the biplot. Take a look at this now. You know what I have right now? In this biplot, we plotted 2 principal components. In a biplot, we can only plot 2 at a time. 2. Okay. And what do you see inside the plot? Those are the weather station in Canada. Those that are close together, like Victoria, Vancouver, they are actually experiencing the same weather condition. Does that make sense? They're experiencing the same weather condition, and when you take a look at Winnipeg and so on like that, those are the upper north. They are also enjoying the same weather condition. It may be cold there and maybe very mid in the other one. So the idea of using a biplot, one of the reasons is for you to be able to see the position each data point, okay, is in the, the principal, what I'm going to say, the principal component space. Now, I need you to pay attention to this guy now. There's another biplot for the same Canadian temperatures. What is the blood dotted line? The black point. The black point, they are the cities that I talk about, the weather cities. Okay. And let me tell you this. The far a point is away from the origin, the more it contributes to the variability in the data set. The more a particular point is away from the origin, the more it contributes, the more the contribution to the variability in the data set. Now, let me tell you this. What is this? Oh my God. Those are the variables. Those are the variables. When the variables are in the same direction, that's a positive correlation. When they are in opposite direction, that would be a negative correlation among the variables. If I want to talk about it in terms of angle, let me talk about it in terms of angle. I needed to take a look at this. The more they are compared together, if the angle is very close to 0, that's a positive correlation too. When when the angle is 90, I want to award an extra credit because exam is coming. Can somebody tell me when the angle is 90? What does that mean? What is interpretation? Go ahead. They are independent, which means they are orthogonal. They are all related. Send me a message for extra credit when the angle is 90. But what if in a situation where the angle is 180, very close to 180, they are negatively related. That's what I mean. When the angle is very close to zero, they are positively related. When the angle is very close to 180, they are negatively related. When the angle is very close to 90, they are orthogonal. This is actually enable us to have interpretation, even though we know the principal component analysis as an interpretability issue, but the biplots will enable us to make a sense of some interpretation. Now, you can see that, right? Okay, last slide. Some useful code, but you know what? My TA is going to walk you through how to, how to implement our principal component analysis in our, like I said, I'm going to release exam one practice question with solution tomorrow, Saturday. And of course, next week will be dedicated to revision. So I'm going to tell you what you're going to bring to the exam, the mode of the exam, and the expectation, and so on like that. Of course, this week is going to be dedicated to that. So this way, I'm actually going to stop today. Make sure you all stay safe and have a lovely day. Bye for lovely weekend. Today's Friday. Right. Okay.